So now that we've learned a little bit about the basic descriptive statistics, we're going to think a little bit about how we make inferences about populations. Again, this is simply a short overview of what really often takes a much longer time to teach thoroughly, but hopefully this will give you enough of a sense to understand what we're going to be doing when we start looking at data and start to actually make inferences about populations from the data that we have collected. So again, looking back at the example we saw before, here is an actual variable that was collected as part of the 2012 ANS that reports the number of days in a typical week that people, the respondents are reading news on the internet. Here you can see that the median, the mean is a 3.57, the median's a 4, the mode's a 7. We also have standard deviation. We can also see that there were almost 5,600, little over 5,600 cases were collected here. But of course, we've only got 5,600 people out of a huge population of, 200 million plus sort of voting age population in the US. So what we want to be able to do is go from the data that we have over here, right, to inferences about the entire population. Because right now we only have 4 or 5, examples here on the thing, but we've got, 5,000 people. So how likely is it that we got the right answer, and how confident can we be that our answer is a good description of this entire population? And that's really the goal of inferential statistics. So again, internet using the American population is our estimate of 3.57 days per week likely to be correct. And the answer is thankfully yes, basically assuming that we have an externally valid sample and that we've also used weights appropriately. And that's thanks largely in large part to the law of large numbers is what it's called, which basically says as the sample size increases, the mean of the sample converges to the population mean. So again, the basic insight here is that if you happen to only choose 5 or 10 people, they might not look that too much like the rest of the population. But as you choose more and more people, the chances of, as long as these are being chosen randomly, or in a way that approximates, I should say. So it turns out there's a lot to be done to choose randomly. But imagine them instead being, say, there's 1,000 pieces of paper in a jar, and they have different colors on them, and then we're trying to, in essence, pull out the different colors. So that's the more standard statistics example, but the real point is as we get more of those, up to a point, so basically by the time you've got around 100 or 150 observations pulled from the population, you actually can feel pretty good that this that you're very likely to be, the sample mean should look a lot like the population mean. Now, we might want to, though, be a little bit more precise about what we mean by how good is that estimate and be able to calculate something that looks like a confidence interval using the standard error of the mean. And the reason for this is, in essence, or obviously the reason is that we want to be able to say we've got this sample mean of, say, 3.57 days, and that's going to be plus or minus, say, 0.5 days, or you often hear, support for some candidate is, 47% plus or minus 4%. So those are the types of confidence intervals. Basically, we think on average we expect support to be around 47% of the population supports a certain candidate, but we know that our sample might not still be perfect, and so we have some interval within which we think that the real number falls. And the reason that we can do that in the underlying mathematical principle that we're using is something called the central limit theorem. And the idea is that basically, if you have these independent variables that are being pulled out, then they're gonna the sum of them, or i.e. the mean of them in essence in this case. So the means of the different populations is going to be distributed normally, regardless of the underlying distribution of the variables themselves. Now, what does that mean? We saw that in our original watching TV, we saw a binomial distribution where most of the people were at 0 and most of the people were at 7, but our mean was around 3.5. Well, it turns out that if I draw over and over again, say samples of 1,000 from the original 5,600, and I calculate the sample mean for each of those samples, what you can actually see here is that if we treat our 5,600 observations as the population and we treat our little samples of 1,000 as our quote-unquote sample, what you can see is that even though the underlying distribution of the variable was bimodal, as we saw before, here we get this very nice normal-looking distribution of the sample mean. It's a little bit counterintuitive, but it does sort of make sense that in essence, because we're tending to get the right answer, in this case it should be around 3.57, right? Sometimes we get further away from that, as far away as 3.5 or 3.7 in very, very rare cases, but most of the time our answer is going to be about correct, depending, again, on the actual observations or sample that we draw from what we're considering as our larger population. Now, many of you have seen this before. We can actually be more precise about where different observations are likely to fall. And this is going to be a standard bell curve or normal distribution here. We'll often be using a T distribution, which has slightly fatter tails, but it's going to be very much like a normal distribution. It just tells us, in essence, what we can figure out from this is once we know where the mean is and we know the standard deviation, we can start making claims about the proportion of samples that we would expect to find. So if we resample the population 100 times, what proportion of it would fall within sort of different confidence bands? And so what you can see here is that between, if we think about this as a standard normal where we've in essence got different types of standard deviations up and down, you can see that around 68% of our samples are expected to fall within one standard deviation of the true population mean. 95% are expected to fall within two, and around 99% are in fact expected to fall within three. So it's pretty nice that now that in essence we have used this law of large numbers, we can now start to say, okay, once we have whenever we need to go collect confidence intervals, we can say plus or minus 2 standard deviations away from the mean. And that should give us a 95% confidence interval. And again, I'll look at that a bit more closely, but the underlying idea is that each sample is like this unique draw from this true population, and therefore we can we're making inferences back about what the actual population mean is. So just as a reminder, the standard error of the sample mean is not quite the same as the standard deviation of the underlying variable. Because in fact, what you have to do is you take the variance of the sample mean and then divide it by the size of the sample, or n, and actually you end up having to divide it by the square root of n whenever you talk about the standard deviation. Because as again, we get larger, basically back to our original point, as we get, the law of large numbers says as we get larger samples, we're more confident that we're getting the right mean. We're better at estimating the mean. It's converging to its true value, and we want to take that into account when we calculate the standard error. So that's the reason that the standard error of the mean is slightly different than the standard deviation of the sample itself. Now, this is just some background that we've gone through. So now we want to actually start figuring out how do we calculate these actual inferences. So we want to be able to make claims about the mean that we observe, and we want to be able to really make two types of claims. I've talked about the confidence intervals. We're going to take a closer look at how to do that, but we might also test null hypotheses. And so for that, we're going to be using basically a t-test. So one type of hypothesis or inference we might want to make is average internet use for news greater than 3 days per week in the population that we're observing. So for that, what we're going to do is calculate this thing called t. We're going to take the actual observation that we have, which we're going to call h alt, and our null hypothesis would be 3 days per week. So we fill that in the place of HO, and then we're going to divide it by the standard error of the mean, which in this case we've calculated as 0.046. If you went back to the original table, you should see that if you take the standard deviation, you divide it by the square root of n, you should get 0.046. What you can see then from this t statistic is that the t number is 12.44. Now, thinking back to what t is that t is in essence the number of standard deviations away from the mean. So again, if you think about the fact that you're dividing it by the 0.046, that just is the standard error of the mean. So if the answer was a 1, it would be 1 standard deviation away from the mean. If it was a 2, it would be 2 standard deviations, and so on. We've got 12 standard deviations. This means it's really, really far away 3 is really, really far away. It's 12.44 standard deviations away from 3.57. Therefore, it's well outside the confidence interval. And in addition, we can feel very, very confident that it is greater than 3 days per week. So visual interpretation then is this is just how far away 12.44 is, a T of 12.44 is from the 95% confidence interval. It's well outside of that. So in essence, the probability that it's, we can, in essence, feel, getting back into how we're going to actually say these things, I've often talked about this some in class. It gets very tricky whenever you're rejecting null hypotheses because you never prove anything to be positive. What you do is you end up rejecting null hypotheses. So again, we'll talk about more about how you word it and phrase it in class. It gets definitely a little bit tricky. So in essence, then if you have a t statistic that is larger than 2, what are you doing? Are you rejecting the null? Are you rejecting the alternative? Are you confirming the null? Or are you confirming the alternative? We'll think about that for a second and then describe it. So the answer here is that you can reject the null hypothesis, that it is only 3 days, and that you can actually redo things and actually claim that it is in fact larger than 3 days, but that's a slightly different test. So a confidence interval is going to give us this estimated range of values, again, plus or minus some number. And the way that it gets calculated is plus or minus around 1.96. I often just, as a frame of reference, I think 2 in my head. Plus or minus 2 times the standard error of the mean. This, the t statistic can be found in a t-table. But basically, again, the rule of thumb is if you have the standard error of a mean, you just say plus or minus around 2. And that gives you the 95% confidence interval. It actually gives you slightly more than 95%, but it's approximately that. So again, just as a reminder, the difference between standard deviation and standard error is that standard deviation is describing the observed distribution of data around the sample mean, but standard error refers to the standard deviation of the estimated sample mean. So it's instead of describing the actual data, it's about the standard deviation of the estimate of the sample mean. And it assumes normal distributions of sample means because of the this combination of the law of large numbers and central limit theorem, and it's proportional to the square root of the sample size. So standard error of the mean is going to do what as sample size increases? I'll give you a few seconds to think about that. Feel free to pause if you want to think longer. But for those of you who come up with an answer, hopefully you notice that in general, as the sample size increases, that the standard error of the mean is actually going to decrease because it's going to be getting divided by a larger and larger number, very much as we found before with standard deviation.